Okay, hello everyone. Welcome to the lecture, and please confirm that you can hear me clearly and watch my screen before we start the lecture today. Thank you. Thank you. Okay, so last time what we were talking about, we were basically talking about how we can represent negative numbers in binary form, right? And then we did some exercises, or we saw some examples to do that. So today we are going to start again with an exercise so that actually it will help you to refresh your memory, and then we will continue from that point, right? So let's start with the exercise. So here we want to find 2's complement of decimal number 12 in 8 bits in 2 minutes. Okay, so go ahead, start finding the 2's complement form of number 12. So which basically mean you are required to find the binary of -12. Okay, and you need to generate the binary in binary consisting of uh, 8 bits. So 8-bit binary of -12 number. Go ahead and do it. And by the way, today I will try to go a little bit faster because in previous two lecture I was going too slow. So, but it doesn't mean that I want to compromise your understanding. So whenever you have a question, you can stop me. Okay. So I'm also doing same thing. Okay, Ravi, we will see in a minute. Okay. We will see. Uh, okay. Thank you for letting me know that you are done. Let's wait like uh, some other people to also complete. Okay, good. Good. So now let's have a look at this. So we need to first find the 12-bit binary of number 12, right? So which is, uh, if I read from the most significant side, 4 zeros, then 1 1, and then 2 zeros, right? Then how I can find its 2's complement? By flipping all the bits in the binary and then adding 1 to it. So when I flip all the bits, I will get this number, this bit pattern, and when I add 1 to it, so I will get 410100. So Ravi, your answer was little bit different. Do you understand now how to get it correctly? If not, let me know and I can try to explain it on the on OneNote. Are you there, Ravi? You want me to explain it on OneNote, or now you understand why your answer was little different from what I'm showing on the screen? Okay. So now is the example clear to you? Okay, thank you. So, okay. So now let's have a look at another example. Let's say we want to do a minus b, we want to subtract b from a, right? So we can rewrite it as a plus minus b. Everyone knows this, right? So, for example, let's say you have binary number 1 0 0 0 1 and the binary number 0 1 0 0. So basically in decimal, this is 1 and this is 4, right? So you are saying 1 minus 4. And here you are right, so you are writing the binary of both 1 and the 4. But you can rewrite it as 1 plus and then negative of the binary of the -4, right? But how we get the binary of -4? Not by putting minus sign, but by actually first getting the ones complement and then adding 1 to it. So when we get first ones complement of the binary of 4, we get 1011, and then we add 1 to it. So when we add 1 to it, we get this bit pattern 1100. So now this is binary of 1, this is binary of 1, and this is binary of -4, right? So now you can add them together. So when you will add, you will get 1101. So remember last time I explained to you how to add the binary numbers, right? So when you add two binary numbers and like for example, let's say 1 and 1 and the result is 2 are greater than 2. So you convert back it into the binary form and then rewrite it, right? So when you will do it, you will get 1101. Maybe I can do it quickly here. So you get 0, 0, 0, 1, and this is binary of 1, and then I write binary of -4, 1, 1, 0, 0, and then I add, so this is 1, this is -4. Then I add both binary numbers, so here I will get 1, 1 plus 0 is 1, 0, 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1. So I get this bit pattern, right? Now, if this bit pattern represents a signed number, so how will I interpret it? Remember, if you remember from the last time, we said if it is a signed bit pattern, then the weight of the most significant bit is negative, right? So the weight of this bit is 1. So 1 times 1 is 1. Next bit is 0. So we can directly write 0. So 1, 2, and 4 plus 4. And the weight of most significant bit is negative. So it is -8. So when you do the math, you will get -3. So 1 minus 4 is -3. So this procedure is correct. Okay. Any questions here? Okay. Now remember last time we I explained to you how can we find the range of values which is represented with by let's say by 3-bit pattern, 3-bit signed pattern, right? And if you remember it, we said that 3-bit signed pattern, it represents the range values in range -4 to 3, right? So if I simply extend that example from 3-bit to 4-bit, so the range is then definitely larger as compared to -4 to 3, right? So if it is it is a 4-bit number, so what are the all 16-bit all 16 combinations of those bits? 0, so all 0, 0, 1, 1, 0. So you can repeat this pattern, right? So this will represent 0, this represents 1, this represents 2, 3, 4, 5, 6, 7. So all these bit patterns, they represent positive numbers, right? Why? Because most significant bit is 0, right? So they represent 0, 1, 2, 3, 4, 5, 6, 7. And then when you make the most significant bit 1, remember what did we say? The weight of the most significant bit is negative. So it becomes -8 plus everything is 0. So it is basically -8, right? The next bit 1001, so most significant bit has weight of -8, -8 plus 1, 1 this one, right? -7. This is -6. This is -5, -4, -3, -2. So if you want me to do it, actually, I don't want you, I want you guys to understand it clearly. So maybe I can go to OneNote and where is, yeah, this one. I can create a new section. So week 2, day 1, page 1, right? And yeah, now uh we have what is the minimum value smart, sorry, 0, 0, 0, 0, all zeros, right? This is the maximum and the other maximum value is all ones, right? And in between you will have value, let's say 0, 1, 1, 1, right? And then when you add 1 to this bit pattern, you will get 1 0 0, which is the next bit combination, and so on, like 1 0 0 1 and so on, right? Now, when you convert it in the decimal, I think everyone agrees I don't need to convert it. Like, I don't need to go through all the process, but everyone understands that it will be equal to 0 in decimal form, right? I'm just writing here decimal, right? And what will be this one? So remember, we are interpreting all these bit patterns as what? As signed numbers, right? So the weight of the most significant bit is negative, but most significant bit itself is zero, right? So zero into minus 16 plus 1248, not 16 actually, it is 8. Minus 8 plus 7 plus, not 7 again, my mistake, guys. 4 plus 2 plus 1. So this is equal to 7, right? And then this one is equal to what? 1 into raised to 1 into minus 8, which is weight of the most significant bit, plus 0 plus 0 plus 0, which is minus 8. What is this one? Minus 8 plus 0 plus 0 plus 1. So minus 7. And I don't want to go through all of them. So what will the value of the last one? Weight of the most significant bit is negative. So minus 8 plus 4 plus 2 plus 1, which is minus 8 plus 7, so minus 1, right? So what is the range? Now the range is, what is the smallest number which we can represent? It is minus 8, right? So it starts from minus 8, minus 7, right? And then it goes to minus 1, and here it is 0. I'm simply drawing it on the number line, and then it goes up to what? 7. So the range is from minus 8 and less than equal to 7. So it's the same thing they have represented here in the circle, in the form of this circle, right? So here you have all these bit patterns written on the outer side of the circle, right? And inside you have the values these bit patterns are representing, right? The point here is that when you go from bit pattern 0, 1, 1, 1 to 1, 0, 0, since we are saying that bit pattern is a signed number, so from after 7, it is not 8, it is minus 8, because sign of the most significant, weight of the most significant bit is negative, right? So range is from minus 8 to plus 7. So there is an overflow. When you add 1 to 7 here, so you don't get 8, you get here, when you add 1 to 7, you don't get 8, you actually get minus 8, right? And similarly, when you subtract 1 from minus 8, you don't get minus 9, you get 7. So 5, when you subtract 1 from this one, so you get 7, not minus 9. Why? Because these are signed numbers, and most significant bit has a negative weight. Okay. Any questions? No? Okay. So until now, we have seen how we can convert numbers into the different systems like binary, octal, hexadecimal, and decimal, right? Or how we can represent them in those different systems. But how, other than numbers, definitely we have also different characters. So all those characters which are written on our keyboard in our computer, they are represented uh, in the computer hardware using codes, binary codes, right? So this table actually shows those codes for all of the characters, but not in binary form, but in hexadecimal form, right? So for example, if you look at character A, right? So when you press key, when you hold the shift key on your keyboard and press A character, so the code that is generated and which is sent to your computer hardware is 41 in hexa form, right? So in hex form, which basically means if you want to convert into the binary, how you will convert? You convert each character in the hexa form into 4-bit binary, which will be equal to 0, 0, 0, 1. 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 So this is 4-bit binary for 1 and then 4-bit binary for 4, which will be equal to 0, 0, 1, and then 0. So this 8-bit code will be stored in your computer hardware when we press the capital A on our keyboard. And same is the case for all other characters in this table. So when any of these characters, for example, when you press the percentage sign, so the hexadecimal form of hex code of 25 is generated, and then whatever its equivalent binary is, that is stored in the computer hardware. Is everyone clear on that? So this is how we represent different characters by coding them into the in binary form or hexadecimal representation, and storing that representation or code in the computer hardware. Any questions? Okay, if no question, then let's try to do this example. What ASCII code in hex will be generated when you press character H on your keyboard, and what will be the binary form stored in your computer hardware? So you can refer this table and try to answer the question. So when you press H, capital character, what hex code will be generated and what binary will be stored in computer hardware? You have 1 minute to do that quickly. Let me know when you are done. Okay, good. Thank you. Nice. So I don't want to go to OneNote to do this exercise, but because it takes time to like switch forth and back, and I don't want to waste the time. I'm writing the answer here. If the answer you have found is different from what I'm writing, please let me know and then I can help you. So the binary code hex will be 48, binary will be 01001000. Okay. If you have a different answer, let me know. Okay, now let's do exactly same thing for the small character H. So if you have exactly same thing for small character H. Thank you. Okay, I'm waiting for 3 more people to let me know that they are done, and then I will proceed. Thank you. Thank you. Thank you. Okay, this time hex is as clear from the table is 68 and binary is 01101000. Okay. And if you have a different answer, then let me know. I just, it doesn't mean that I want to call you out for that. I mean, I just want to help you to understand the right answer. Okay. Okay. So with that, we are like basically done with the week one, day one, right? So we are going too slow. Today is week. This is what I was planned to be from now on was the material that was planned to be covered for today, week 2, day one. Okay. So today we are going to talk about the internal organization of components in the Atmega 328 microcontroller, right? And we will be talking about at very high level. So what we are going to cover about is what are the different components in the the main components in the microcontroller chip, I/O memory and CPU, how those components are parts they are connected, which mean how memory is connected to CPU and how I/O devices, input output peripherals, basically how they are connected to the CPU and how a computer works. So we will have a look at an animation at how when a program is executed on that microcontroller, how things work, what is like execution flow, okay? How data is moved around and how arithmetical logical operations are performed. So let's first have a look at the components in a computer. So uh, in the microcontroller, we are basically talking specifically about the microcontroller at Mega 328P, but in general, these components are also like necessary part of all type of processors or microcontrollers. So first thing is that you have a central processing unit, right? And this central processing unit is we will have a look at the internal architecture of this central processing unit, and we will see how it helps or how it executes the an example program, right? Other than that, this CPU accesses the data memory, right? So here you have RAM, random access memory, which is used to store the data. Then you have a program memory. So program memory is this one, flash ROM, right? And actually in this microcontroller, you have separate memories to hold your data and to hold your program, which is not the case in your general purpose processors. Okay. And by the way, purpose processors don't have all these components. For example, CPUs and memory on the same chip. So like in your desktop systems, you have separate chip for a CPU and a separate chip for memory. And the other thing is that this microcontroller, it uses RISC architecture. Again, we are not at going detail of RISC at this time point. So we'll talk about RISC architecture, like what are the features of RISC architecture, maybe in next lecture. Okay. But I will try to cover these three components today. Okay, CPU, central processing unit, it is responsible for performing the logical and arithmetic operations, or basically it is responsible for executing the instructions. And those instructions can be like, example of those instructions are logical instructions and arithmetic operations, right? Memory, it is responsible for storing the data and recalling the information. So, for example, RAM or hard disk in general purpose processor. In microcontroller, definitely you don't have a hard disk or a piece of paper, not in digital world, but like in from daily life, it is an example of memory because it is a piece of paper is also a device which you can use to hold the information, right? Input and output devices are input output peripherals. So examples of devices which can provide input to your computer or to your microcontroller, they are like keyboard, mouse, or some type of sensors. And output, the data generated by your microcontroller, you can display it on a monitor or on a screen, or you can send it to a printer, or you can use that data, or you can actually display that data by movement of a hand of a robot or by movement of a wheel on a car, right? So, uh, by the way, please feel free to stop me at any point. Here at this time point, I don't have exercises because this is like more kind of what I covered in couple of previous two slides was more of kind of theoretical things. So I don't have examples here. So, but stop me if you don't understand anything. So we talked about CPU, right? Now let's have a little bit, very small discussion about memory. So we said that memories, they are used to hold the data or to hold the program, right? So how we represent the capacity of a memory. The capacity of a memory is represented by number of bits that a memory can store. For example, if I say that I have a memory chip with a capacity of 128 kilobits, it's basically mean that the chip can store 1 to 28 times 2 raised to power 10 number of bits, and 2 raised to power 10 is 1024. You can do the math. So whatever result comes, that it means that chip can hold that number of bits. Okay, and each bit can have only value of 0 or 1. Okay, Now, as another example, let's say if I have a memory chip with capacity of 256 megabits, so it's mean that it can hold 256 times 2 raised to power 20 bit number of bits. And 2 raised to power 20 is basically 1024 times 1024. So you can do the math and you will find how many number of bits can be stored in that chip. Okay, so this was basically about how we represent or how we can specify the capacity of a bit. So capacity of a bit is specified in number of bits, right? But how a memory chip is organized internally, right? So memory locations are organized internally in number of locations. So for example, if I say that I have a memory with an organization of 128 cross 4, what does it mean? It means that the memory I'm talking about or the chip I'm talking about has 128 locations, and then each location can hold 4 bits. Okay. So this is how it looks like. So you have 128 locations shown like in form of rows, and they are numbered or addressed using addresses 0 to 127, right? And then each bit here, each location here can store 4 bits. So the organization of the memory is that's why we say 128 cross 4. The third characteristic of a memory chip is access time, which is basically time to read the data from memory, right? So, this is typically specified in nanoscale, so a nanosecond scale. Why? Because the speed at which the memory is read is very fast as compared to like in human perspective. So 1 second, how and what is 1 nanosecond? So one nanosecond is basically 1 second equal to 10 raised to power 9 nanoseconds. So 1 nanosecond is 10 raised to power minus 9 seconds, right? So it is like 10 raised to power ninth part of a second. Okay. So 1 second, as I guess you already know, is equal to 1000 millisecond. 1 second is equal to 1 million microseconds, and 1 second is equal to 10 raised to power 9 nanoseconds. Okay. Any question at this point? Okay, if you don't have a question, then I have a question for you. Here we are saying that access time is defined as time to read the data from memory. Why we are saying time to read the data from memory? Why we are not measuring access time as the time to write data to the memory? Why access time is defined in terms of read time and not in terms of write time? Any guess? Is it because writing time isn't always the same? Uh, let's assume writing all time is always same. There can be situations where writing time can different because of memory conflicts, but same is the true also for reading time. Reading time can also be different if like there are, you try to read from cache. If data is there, you read it faster. If data is not there, you go down, it takes time. But let's forget those issues. Let's say that read and write time is always the same. Then why we are defining access time as read time, not as write time? But that's a nice, uh, at least you are trying to think. Okay. Let me tell you why that is the reason. Okay, someone also answered because it is done from the point when you reach out to the memory. Uh, I didn't understand what you mean by that. There is no name, so I don't know how to call you, but I don't understand your point. Would you like to elaborate a little bit? Ah. Okay, okay. Yeah, let me explain. Let me explain. So basically, it has to done uh, with the fact that read are critical but write are not critical. What does it mean by read are critical and write are not? Write operations are not. So let me show you then. So let's say you have this CPU, right? And this CPU is running a program, and I'm writing that program here. So let's say that program is uh, write data from register 1 to memory location X. And after that, the next thing to do is write uh, R2 is equal to R1 plus R3, right? So let's say the value of R1 is 10, right? So, and this CPU is connected with the memory, right? So what will happen? CPU will place the data on value of 10 on the bus. Will send the data of a value of 10 to the memory, right? And then after the next instruction it needs to do is add the value of R1 and R3 and put the result on R2. Now the question is, does the CPU need to really wait until 10 is actually written into the memory, or it doesn't need to wait and it can go ahead and start executing the next instruction? Anyone who want to answer? Let me repeat the question. Does the CPU really need to wait until the value of 10 is actually written into the memory here and only then start executing the next instruction, or it doesn't need to wait as soon as it places the data on the bus, it can go ahead and start executing the next instruction? Or does it need to actually, I mean, it doesn't need to wait. Anyone who want to answer that? You can actually unmute yourself. Talking is faster and more like give you a real life. It's the CPU doesn't need to wait. Yes, it won't need to wait. Yeah, that's correct, right? It doesn't need to wait. Why? Because it doesn't. Why it doesn't need to wait? Because it doesn't need this data anymore, right? I mean, it doesn't care whether the next instruction is not impacted by the fact that whether the data has reached in the memory or not, right? Now, let's consider another scenario, right? So let me draw it here. Again, let's say you have CPU and it has a program. And here you are saying R1, move the data in R1 from memory location X, right? And then you are saying R2 is equal to R1 plus R3, right? So X is the address of the memory location and your CPU is connected with the memory. So this is memory. And here you have two buses. This is, let's say, your data bus on which data is placed, and this is address. So what does CPU do is that when it executes this instruction, it places the address. Let's say the address is, I don't know, let's say 100. So it's basically saying read the address value from the location 100 of the memory and put it in the R1. So it places address 100. So can now CPU, after placing the address 100, can it go ahead and start executing the next instruction or not? Anyone who want to answer? Yeah, it has to wait. Why? It has to wait because the execution of next instruction actually needs the data to become available from memory and placed in the register R1, and only after that it can use that result here and do the addition and put the result in R2, right? So, which means that write is not on the how to say, on the critical path, right? Write operation is not on the critical path, but read operation is on the critical path, which means that you need to wait for the read operation to complete before you can go ahead to the next instruction, right? But for write are not, they are off the critical path. right? So we don't need to like wait them for to complete before we go ahead. So since read is critical, that's why we measure the latency of the memory chip in terms of read operation, not in terms of read write operation. Okay. I hope it was helpful. I mean, I know from like the perspective of this course, maybe it was not necessary to explain, but I just wanted to address that point. Okay. So now the question is, we have seen that in the previous slide, what are the characteristic of memory in terms of capacity, in terms of organization, in terms of access latency. The question is now how we connect a memory chip with the CPU, right? So if you look at the memory chip, you have typically this set of buses. First, you have a VCC signal, which you always connect with the power supply. You have the ground line, which you always connect with the ground signal, R0, volt 0. Uh, then you have, uh, other than that, you have data bus, you have address bus, and you have three control signals, right? So the job of the, let's start with the control signal. The job of the control signal is chip select. Here CS stands for chip select. So chips, the value, the job of the chip select is to tell the memory chip that you are selected. You are selected mean you are enabled. So whatever address is placed on the address bus by the CPU is for you, right? So it's mean that you are enabled. You should be in working mode. So and what is meaning of this line or bar on top of CS chip selects? It's mean that this chip select is active when the signal placed here on the line is 0. So which means that if the signal placed on the line is 0, then the memory chip is selected. But if the signal or value placed on this chip is the value of the bit line is 1, then it's mean that memory chip is disabled. Okay, it is not selected. So whenever any signal has a bar on top of it, it's mean that it is active low. So it will achieve its purpose when the driving value or the value on the input line or on the line is 0. Okay. So OE, it stands for output enable. And again, you can see there is a bar. So which basically means that this signal will be work when the value here is 0, right? And what is the purpose of this signal output enable? It's mean that the, it can place, this memory chip will be able to place the data, whatever data you want to read from it, it will be able to place the data on its output lines only when this signal is 0. This one is 0, okay? And write enable, again, this is low active low signal. So whenever you place 0, only then this you will be able to write data into the memory. Okay. And what is the job of address lines? So address lines, actually you used them to select a location within memory. If you remember here, for example, in this particular example, you have 128 locations. So you use the address line to specify the location from where you want to read the data, or the location to which you want to write the data, right? And then these data lines, these are the lines, for example, when you are writing, so the CPU will place the data on these lines, CPU will place the address on these lines, CPU will set this chip select equal to 0, CPU will select this one equal to 1, because output enable mean read enable, but we want to write, and CPU will set 0 here. So then what will happen, that whatever address you provided, let's say you have provided the address 10, and whatever, and let's say the data you wanted to write in the address 10 is X. So X will be written here in the location 10. Okay. And when you want to read, then what will happen? So you will use a different, let me simply change the color. So let's say if CPU want to read data from the memory, so again, this will be set equal to 0, so that memory chip is enabled. Now output enable will be 0, which is basically read enable. And write enable will be 1, which means write is not allowed, right? And then you will place, the CPU will also place the address on the address bus. Let's say the address you placed is, I don't know, uh, let's say use the same address. So then the value which was written previously at the location 10, which is X, will be placed by the memory on on the data bus X, and then it will be picked by the CPU and placed in some register. Is it clear? Yeah, thank you. Okay, so actually this is the same thing which I have explained to you in the previous slide, but let me just read it for you. Okay. So the memory pin out. So VCC is your positive power supply voltage, common collector to the integrated circuit. So you connect this, always this with the like power supply. This is ground. D0 to D7 is your data bits, 0 to 7, right? Address bus, address bit 0 to n minus 1. It depends how many, like basically it definitely changes depending upon your size of the memory and the organization of the memory. So in previous example, we had 128 cross 4. Let's say if it is 25th, 256 cross 4, then you will have how many? You will have 2 raised to power. You will have like more address bits. I will tell you, show you later how many address bits we will need if there are 256 locations and how we can find it, right? Write enable, which is basically allows the write operation, output enable, and chip selection. Okay, so how so now we have seen that how CPU and memory, they are connected, memory chip, they are connected together. But what is the sequence? I said, like, for example, if you want to read, you need to place the address, right? You read to enable the output enable signal, you need to enable the chip select, right? But what is the sequence of these signals? Do we place address, output enable, and chip select at the same time? Or in a different order, like one after the other? So for that, if you want to read the memory, so what you will do is that first you will put the address on the address line. So let's say you want to read from the address 10, so CPU will put the value of at 10 on the address bus, right? Not, but then there is some delay, right? And after that delay, the CPU will actually drive 0 on the chip select line, right? Why we are doing that? Why there is a gap? Because there is a circuit here which is not shown, and it is called address decoder. That circuit can be like internal to the chip or it can be external to the chip, and that circuit takes some time to process or to decode this address, right? That's why we put some gap here. How much gap? It depends upon from memory chip to memory chip. When you go and you read the data sheet of that memory, it will tell you what should be the difference between time difference between like putting the address and enabling the chip, right? After enabling the chip, you wait for some more time here, basically this time point, this time duration, and then you drive the output enable to 0, right? And when you do that, so then it will take some time, and after that, the data will be available from the memory on the data bus. Okay. And your time memory access latency is defined as the time point from where you enable the address, you place the address to the time point where your data actually became available on the bus. So, which is this duration here. So, this is known as your operation. What does it mean by same goes for the right operation? Which means that if you are, let me actually delete these uh, annotations. So let's say now if you want to do the write operation, so then again we need address, we need to enable write enable line and chip select. But can we place the address, write enable and chip select at the same time? No, there needs to be a sequence. So first what you do is that you you place the address, then you after some time, which is like here it is shown to be very small difference. You enable the chip itself by driving 0 on the chip select signal, right? And then after some time, you drive the write enable to 0, right? And then your data, which you are, after some time, after write enabling, you place the data which you want to write on the memory. So let's say again, if you want to write the value of 10, let's say value of x and address 10. So first you will put 10 here, right? Then you will drive this 0, 0 on this line, you will drive 0 on write enable, and then you will put the value of X here, and then that value will be after you place the value on the data bus. So you need to wait for this period of time, data setup time and data hold time, and after that this value will be successfully written in the location 10 within the memory. Okay. So the takeaway here, you don't need to worry about the sequence, but you just need to know that you cannot drive all the required values on all those lines at the same time. There is a delay between them when you place the required values, and there is a reason behind having that delay, and the reason is that address need to be first decoded by your address decoder, and the amount of the delay is specified in the datasheet of each memory chip. Okay. Any questions? Okay, we have seen how we can connect memory to the CPU, right? Now let's have a look at how we can connect I/O devices to the CPU. Let's say you have a mouse, you have a keyboard, you sound card, graphic card, network card, and you need to want to connect all of them with the CPU, right? So if like we connect all of them separately, right, using separate connections or separate pins on the CPU, it's mean we need so many pins for each one of them, right? It depends how many pins are needed for mouse. I don't know. Let's say 3 pins. Then for keyboard, I don't know. Maybe I'm just making up a number, 10 pins. Similarly for sound card. So what happened? We will end up having so many pins on CPU. And the problem is that more the number of pins you need on a microcontroller or CPU, more expensive it is. And not only expensive, its size of the chip also increases. Okay. So we don't want to have that situation where we have separate pins or connection for each of the IO device or input output device. So if that is the case, then how can we support these diverse type of IO devices, but keeping the number of pins, input output pins low, right? So for that, what we do is that we have same address bus and data bus connected with all of the IO devices. So let's say if we have 4 different input output devices numbered here from I0, let's say N, not 4, from I0, IO0, IO1 up to ION. So all of them are connected with the same address bus shown in blue and the same data bus shown in green here, right? And then they are like again we can read CPU can read data from an IO device, for example keyboard. It can also write data to the IO device, for example displaying your data on the monitor or on your screen, right? So it's mean that two type of operations can be performed. So now if we are specifying the address, and let's say I'm saying that okay, the address for IO device 0 is 10, right? So okay, it's mean that this device will be selected. But what type of operation I want to do on this device? Do I want to write data to this device? I want to read data to this device, right? So then CPU will basically specify the type of operation by specifying value for these read and write signals. Okay. So, but again, and then how we will know that, let's say if the address which is placed on the address bus is 10, how do these devices know that whether which one of them is supposed to respond, right? So all of those devices, they actually know their addresses. So let's say the address of IO device 0 is 10, address of IO device 1 is, I don't know, let's say 12, the address of IO device 2 is 3. So if the address is 10, so then address IO device 1 and 2, they will automatically know that I am not supposed to respond to this address because this is not my address. I'm not supposed to perform participate in any read or write operation. And IO device 0 will know that, okay, I am going to participate in this communication. Okay. And then it will check read or write signal. So if it is read signal, then it's mean that the CPU want to read the data from the IO device 10. So device 10 will place the data on this bit on this bus, and that data will be then moved into the CPU, right? And if the write signal was active and read signal was not active, then it's mean that CPU will first place the data on the data bus, also the address definitely, and then that data will be written to the IO device 0. Okay. Any questions? No? Okay. Okay, so this is what we have like the covered until now at this point, like how we connect our interface CPU with memory and how we interface CPU with the IO devices, right? But here what we are seeing is basically that we are saying there is a separate address bus for the IO devices and a separate address bus from the memory. And similarly, a separate data bus for the IO devices and separate data bus for the memory. Separate read and write signals for the data bus, so for the IO devices, and separate write and read signal for the memory. So it again we end up in the same situation, which mean what do we I mean by same situation? It means that we have so many uh, lines or pins on the CPU, right? One set of pins for the IO for communication with the IO devices, another set of pin for communication with the memory. So how we can reduce these number of pins but keep both memory and IO devices connected with the CPU? So we can do exactly the same thing what we did here, right? We said, okay, we can use the same same address bus and data bus and read write signal with uh, all the IO devices. And then how IO devices are differentiated from each other based on the address, right? And how operation is differentiated based on the value of read or write signal. So we can do the same thing here. We have same address bus which is connected with all the IO devices and also with the memory, right? And we have same data bus connected with data line of all the IO devices and also with connect data lines or data pins of the memory, and same set of read and write signals connecting with the IO devices and also with the write enable and output enable of the memory, right? And for chip select, we can say that, okay, maybe we can keep this memory selected all the time. So we are like setting it, connecting it permanently to 0, right? And how we can like then differentiate between uh, so if that is the case, then what will happen? What is the problem with that? If we permanently connect it with the 0, it means that your memory will be enabled all the time, right? So whatever address is placed on this, that address will be searched in in this memory, and then depending upon value of the read or write, the data will be written to that address in the memory or will be read from that address in the memory, right? But maybe we don't want it, right? We don't want our memory to be active all the time for all the addresses, because for example, let's say your number of locations in your memory are, let's say, only 4, 0, 1, 2, 3, 4. Let's say if the address placed by the CPU is 3, okay, yes, we want our memory to be active. But let's say the address placed on the address bus by the CPU is 10, so the location, there are only 4 locations, so it should not be active for address 10, right? So that is the problem here, right? So how do we then manage the address conflict? Uh, like, for example, as I said, if 0, 1, 2, 3 are the addresses placed on the address bus, yes, chip should select should be low. But if the address placed on the address bus is 10, and maybe this 10 is for IO device 1, then this chip select should not be 0, it should be 1 here, right? But if we permanently connect it with the low signal, it's mean that we can't do that. We cannot like dynamically change the value of this input to 0 or 1 depending upon the address in this current connection or in this current uh, uh, configuration, right? So how do we manage this address conflict? So that is what we are going to see in the next couple of slides. Any questions? So one, if we keep our situation simple, simple mean if we assume we have only one memory chip, then what we can do is that we can, from the processor side, we can generate an additional signal, which we are naming it as IOR memory low, which basically mean that, and we are connecting the same line with all the IO devices and with the chip select of the memory. And here, if you note, we have a bar on mem, which mean that if we drive zero on this CPU places zero, it's mean that it is selecting the memory, right? And if it places one on this line, it's mean that this memory will not be selected, and it's mean that CPU want to communicate with one of these IO devices. Which one of those IO devices? That will be determined or differentiated based on this address bus, based on the value of the address placed on the address bus. Okay. However, this solution will work only if you have a single memory chip connected with your CPU, which we have like connected are shown in this example that only one memory chip is connected, right? But let's say if and in this example, the capacity of this memory chip is 64. It has 64 locations, and let's say each location can hold only one bit. So its capacity is 64-bit and the organization is 64 cross 1, right? Let's say if I connect another chip with the exactly same capacity here, right? And it can also store 64 location. It has also 64 locations, right? So what will be the total capacity of memory in my system? 64 plus 64, 128, right? So first 64 locations are in the chip 1, memory chip 1. Let me write here MC1, memory chip 1, and next 64 locations they are in memory chip 2, right? So let's say what I want is that if the address generated by the processor is in the range 0 to 63, right, then this chip should be selected. But if the address is in the range 64 to 127, right, then this second memory chip should be selected. But how can I do that if the chip select of this line is also connected with the same signal, right? So if it is zero here, it is zero here, right? Which means that both are selected at the same time, which I don't want. What I want is I want the first one to be enabled if the address is in the range 0 to 63, because it has first 64 locations. And I want the second one to be enabled if the address is in range 64 to 127, right? So this configuration, a solution, it will not work when you have multiple chips connected uh, with your CPU. Do you have any question, any confusion at this time point? I mean, I know it is getting a little bit complex as we are moving forward. We are adding complexity to it. So if there is anything you don't understand, let me know. The problem here is like, to me, it appears that everything is clear, but then I am not at the same level. So maybe there are some things which you think are confusing. If they are, let me know. I try to answer them, explain them. Okay, so if no questions, then let's continue. So how can we then answer this question? Like, how can I do this if address is in the range 0 to 63, uh, and I want to use the memory, but yes, I want to use the memory, but which memory chip I cannot differentiate? How can I like enable my target memory chip just by looking at the address? So for that, what we need to do is do the address decoding. Okay. And how we perform address decoding? What we do is that here, instead of like directly connecting chip select with like write signal, chip select signal coming from the CPU, we can basically put here a logic circuit, right? And the job of that logic circuit is to enable this chip only if the address is in the desired range. For example, logic circuit of both these chips they will be different then. So logic circuit of first chip, what it will do is that it will check if the address is in the range 0 to 63, it will put a 0, send a 0 to chip select. And the logic circuit of the memory chip 2, what it will check if the address range is in the range 6420 to 127, it will send a 0 to chip select. Otherwise, it will not send 0, it will send 1. Okay. So what we do is that we develop a logic circuit, we put it on the input of the chip select. And what is the input of that logic circuit? Input of that logic circuit is the address coming from the CPU. Then definitely it's mean logic circuit is different for different memories, depending upon which address on which address ranges we want that memory chip to be activated, okay, or to be enabled. So now the question is that how we develop that logic circuit. Okay, just give me 1 minute. Okay, so the question is that how we develop this logic circuit. So to answer that, before answering that, we need to first have a look at logic gates, right? Why? Because logic gates are used to construct the logic circuit, which is then used to enable a memory chip. And by the way, those circuits are known as memory decoders or memory address decoders. So to construct memory address decoders, need to use logic gates. So first, let's go through the understanding of logic gates, how they work, and then we will see how we can use them to construct address decoders. Okay. So there are different type of logical gates. Uh, First one which we are going to cover is AND gate. Actually, it implements the AND operation. What is AND operation? So just like, for example, you have add operation, like let's say if I say add operation between two operands, let's say 2 plus 3. So you know what is the answer, right? 2 plus 3 is 5. So you know how the add operation is performed by summing the quantities, right? So similarly, we also can do the AND operation between, not between, actually yes, between 2 and 3. So we can do the AND operation. But now the question is how we perform. Everyone knows how to perform the AND operation because this is what you understand maybe in grade 1, right? But now we are going to look at how we perform the AND operation between 2 and 3, right? So for that, uh, we will come back how to do the AND operation between numbers 2 and 3. But let's first go to how to do the AND operation between two bits, two binary digits or 2 bits. So let's say you have 2 bits, A and B, and the value of the A is 0 and the value of B is 0. So the result of AND operation will be, sorry, I used a different symbol, but in this lecture slides, they are using cross to indicate the AND. Okay. But in like normally in literature, they use this upward arrow to indicate AND. Okay. So the AND operation is like if both input AND operation between two input operands is result of AND operation is 0 if both of the input operands are 0. If one is 0, the other is 1, result is still 0. If A is 1 and B is 0, result is still 0. The output of AND operation is 1 only if both input bits are 1. Okay. If any one of them is 0, result is 0. The result of AND operation is 0. Okay. Now, let me go back to the question how we can do the AND operation between 2 and 3. So to do the AND operation, what you do is that first you convert 2 into the binary form. Let's say I write the 4-bit binary of 2. So it will be 0, 0, 1, 0. And then I write the 4-bit binary of 3, which is 0, 0, 1, 1. And then I do the AND operation between bits bitwise. So AND operation between first 2 bits, 0 and 1, it will be 0. You can check from this table, right? Because both of the we what we require for the output to be 1, we require that both input pins are, or both input bits are 1, right? So for the next two bits, the output will be 1 and operation, right? 1, 1, 1, 0, 0, 0, and operation 0, and then and of 0 and 0 is 0. So this will be the AND operation of between 2 and 3. Okay. Any questions? Okay, if no question, then let me give you an exercise. I'm writing it here. Write a result of AND operation between 4-bit binaries of 7 and 4. You have 1 minute. Okay, thank you. Nice. Uh, Ravi, your answer is incorrect. I will explain. No, in AND operation, there is no carry. In AND operation, it is AND, remember? We are not adding, we are doing AND. Yeah, it's good to ask, Ravi. Yeah, good job. Okay, so yeah, that's correct, Ravi. So, how to do it? 7, what is the 4-bit binary of 7? 0, 1, 1, 1. What is 4-bit binary of 4? 0, 1, 0, 0. Now do the AND operation between them. And for that, if you don't remember, you can check the table. So AND between 1 and 0 is 0. 1 and 0, 0. AND between 1 and 1 is 1. And AND between 0, 0 is 0. So if I convert this bit pattern to decimal, so it will be 4. So AND between 7 and 4 is 4. Okay. Okay. Let's cover the OR gate and then we can stop. Okay. So again, OR operation. By the way, one thing I forgot. So you represent AND operation using this AND gate, and this is the symbol of AND gate. Okay. OR operation. So in OR operation again, you have two bits as input and you have one bit as output, right? And the output is 1 if any one of those input bits is 1. So for example, here we have both A and 0 as 0, so that's why the output is 0, right? But in all other cases where we have at least one bit as 1, input bit as 1, then the output is 1, right? And this is known as OR operation. And here they are indicating OR operation using plus sign. Let's say we also use the same symbol, right? So now let me try to do the same example which I did last time, like OR operation between 2 and 3, right? So what is the 4-bit binary of 2? 0, 1, no, 0, 0, 1, 0. And 4-bit binary of 3, 0, 0, 1, 1, right? So when I do the OR operation, so as long as one of the any bit is 1, input bit is 1, the output will be 1. 1, 1, 0, 0. Okay, which is same as 3 in decimal. Okay, is it clear? So if clear, let's do the same example. Write result of OR operation between 4-bit binary of, mm, let me do it. 4-bit binary of 9 and 5. Go ahead. Yeah, that's correct. That's correct, Ravi. Yeah, good. Good job. Yeah. Okay. Okay. I have a question on the last one. Why isn't with 0 and 0 not equal 1? Isn't in a normal proposition that the case? So that is like you are asking like why is R operation between and 0 is 0 and 0 is not equal to 1, because that is the definition of the R operation. I mean, I don't have a way to answer the why part, because this is how R operation is defined. Huh, not R. And why 0 and 0 is not 1 in that, again, because that is the definition of AND operation. Just like, for example, if I asked you why the result of 0 plus 0, adding 0 to 0 is not 1, because adding nothing to nothing is not 1, it is 0 still, right? In the same way, when you do 0 and 0, it is 0. Because the definition of the AND operation is that output is 1 when all the inputs are 1. Does it satisfy, or you no, you are not? I mean, well, I'm assuming this ties to discrete math. Maybe. Maybe I'm not sure on that, but that is the definition, or that is what I how I understand. Maybe there is more deeper reasoning behind that, which I am not aware of, right? So that's why I don't want to like go in the direction which I don't know. Okay. Okay. So has everyone done with that? Is done with that last exercise? Yeah. So it was, remember what was it? It was again, let me write here, 9 and 5, right? So the binary of 9 is 1, 0, 0, 1, and binary of 5 is 0, 1, 0, 1. Now when you do the R, as long as any of the input bits is 1, we the result will be output, result will be 1. So here 1, 0, 1, and 1. So which is D in hexadecimal form or 13 in decimal form. Okay. Is it clear? Okay, so okay, thank you. So then let's stop at this time point. We have only 1 minute left. So let's stop at this time point, and next week, not next week, in next class, you have the quiz, right? So the quiz will cover the material which we have studied today and in the last lecture, which mean on the last Wednesday, right? So all that material up to this slide will be covered. Okay. So prepare yourself for the quiz and see you in the next lecture. Thank you. Thank you. You too have a nice day.